Hello GATE aspirants, welcome to part 10 of GATE electronics series. Question 3. For the following circuit, what is the magnitude of V out if V in is 1.5 volt? So here V in is given 1.5 volt. This is inverting amplifier since input is given to inverting terminal. So this is inverting amplifier and feedback is given. So VO is equal to closed loop gain for inverting amplifier, that is minus Rf upon Ri into Vin. Rf is 100 R and Ri is R and Vin is 1.5 volt. So this will be 100 into 1.5. So this will be 15 volt, minus 15 volt. So option C is correct. You just have to multiply this by 100. So answer for this question is 15 volt. Option C is correct. Next, question 16. Consider the following Boolean equation. It can be represented by a single 3-input logic gate. Identify the gate. So for that purpose, we have to solve this. So let us simplify it. So we have A bar or B bar. For the second bracket, we can use De Morgan's theorem. So this will be A bar and this AND will become OR, and then we have B or C bar or A, B bar or C bar. Now here again we will use De Morgan's theorem. So A bar or B bar, then A bar, or this will be B bar, C bar, or A, B bar, C bar. Now let us use distributive property. So we will multiply this. So this will be, or I can take this A bar or common and I can write A bar or, and then here we will have B bar or B bar, C bar. Because if this is the case, A or B, and we have A or C, then this can be written as A or, and here we will have BC. So this distributive property I have used here. Then B bar, B bar. So if we have AA, then that is equal to A. So here A bar or B bar C or A, B bar or A, C bar. Now let us focus on first two terms. Here we have C bar. Let us focus on first two terms, this term and this term. So we have this A bar or AB bar, that will be equal to A bar or B bar. So I am going to use this identity over here. So this will be A bar or B bar or B bar, C bar or AC bar. Now here I can take this one common and B bar common. So this will be A bar or B bar in bracket 1 or C bar, AC bar. So that will be equal to 1 only. So this will be A bar or B bar or AC bar. And we can use this property again here for A bar, AC bar. So for A bar or AC bar or B bar. So here I am going to use this property, this one. So this will be A bar or C bar or B bar. Or we can use De Morgan's theorem and write it as A, B, C, or. So this is NAND gate. So we just have to simplify that equation and you will get NAND gate. Or you can use K-map method as well. From there also you will get same answer. Next question. A 3-bit analog to digital converter is designed to digitize analog signals ranging from 0 volt to 10 volt. For this converter, the binary output corresponding to an input of 6 volt is. So it is a 3-bit converter, so N is 3. Let us first calculate resolution. So resolution is equal to V peak to peak or V max, that is full scale voltage, upon 2 raised to n minus 1, or we can write V max upon 2 raised to n. So V max is given, that is 10 volt, maximum voltage is 10 upon 2 raised to 3. So it will be 1.25 volt. So voltage will go from, since it is 3 bit, it will go from 0 to 7. So 0, 0, 0, 1, then 2, 3, 4, 5, 6, and then 7. And corresponding voltages also we will write. First will be 0 and it will increment in this step of 1.25. So first will be 1.25, then 2.50, then 3.75, then 5, 6.25, 7.50 and 8.75. And we want voltage corresponding to 6 volt. That means here this part we want. So the correct option will be 100, this part. So option C is correct, 100. Since if the voltage is greater than 6.25, then it will become 101. If it is less than 6.25, then it is going to be 100 only. So option C is correct. Next question. For the following circuit, the correct logic values for the entries x2 and y2 in the truth table are. So for x2 and y2, here it is given that G is 0, A is 0 and B is 0. And since these are AND gates, if any one of the input is 0, then output is going to be 0. So this is 0, 0. Then P is 1 and C is 0. So output of this AND gate will be 0 and output of this OR gate is 0 and for this OR gate it will be 1. And next we have NOR gates. So we have to check for it. Okay. So if for NOR gate, let us check. If we have A, B, then 0, 0, 0, 1, 1, 0, 1, 1 are the inputs. And for OR operation it will be 0, 1, 1, 1. And for NOR operation it will be 1, 0, 0, 0. That means if both the inputs are 0, then the output is going to be 1. So let us check initial values of x and 1. These are 0 and 1. So if x is 0, that means this will be 0 and this y will be 1. So if we have input 0 and 1, then output will be 0. And if we have 0, 1 here, then output is going to be 0. So this y will change to 0. And then this 0 will go here. And this 0 and 0 will make this 0 to be 1. And again this 1 will go here. Then it will be 1, 1 and output will be still 0. So in the final state, the outputs will be 1, 0. So x2 will be 1 and y2 will be 0. So here option A is correct. Next question, number 43. For a given load resistance RL is equal to 4.7 ohm, the power transfer efficiency eta, that is power load upon power total, of a DC voltage source and a DC current source with internal resistances R1 and R2 respectively are equal. The product R1 R2 in the ohms of ohm square is. We have to solve this separately for DC voltage source and AC source. Let us first calculate for DC voltage source. So for DC voltage source, internal resistance is given, that is R1, and for voltage source this will be in series. So if this is V voltage, this will be R1, and to that we will connect RL. So this will be RL. Now total power is equal to I into V, and current flowing through this circuit will be voltage upon resistance. So R1 plus RL into V. So that will be V square upon R1 RL. And power across RL, that will be equal to I square RL. That is equal to V upon R1 plus RL, the whole square into RL. Now eta as it is defined, this is equal to power across load resistance upon total power. So let's take ratio of these two terms. So PRL upon PT, so this term will cancel out and this will be simply RL upon R1 plus RL. That will be eta for the voltage source. We have to do same calculations for current source. Now for current source, this internal resistance will be in parallel combination. So for DC current source, if this is our current source I, then this is R2 to which RL is connected. Now total power, that is PT, that is equal to current into voltage again. Now voltage, that is voltage across this arrangement, so that will be equal to I into resistance. Now this resistance is R2 parallel with R1, so that will be R2 RL upon R2 plus RL. So this will be voltage into current. So PT is equal to voltage into current. This we have done. Next we have PRL, that will be equal to I square RL, and current flowing through RL, that will be equal to R2 I upon R2 plus RL, the whole square into RL. So from here eta is equal to PRL upon PT, and that will be equal to, this is I square will cancel out. We have R2 here, so R2 upon R2 plus RL. This will be eta 2. And it is given that equation 1 and 2 are same. That means RL upon R1 plus RL is equal to R2 upon R2 plus RL. That means R2 R1 plus RL square is equal to R2 R1 into R2 RL plus R2 RL. So this will cancel out. So RL square is equal to R1 R2. R1 R2 is equal to RL square, and RL is given 4.7. So square of 4.7 is 22.09, which is roughly 22.1, because we have to round it off to one decimal place. So the answer will be 22.1. And the answer range for this question was 20.0 to 22.2. So these are all the questions from electronics part of GATE 2019 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.